The Apple Valley Model Railroad Club presents Modeling Basics 101. This six-part series introduces you to the exciting world of model railroading, covering everything from initial layout design to final scenery. For more information about the Apple Valley Model Railroad Club, visit their website at avmrc.com. Part 3, Wiring for DCC.
Okay, I'm Dan Lang. I'm in charge of DCC operations at the Apple Valley Model Railroad Club. I'm going to talk to you this morning, Wednesday, November 5th, 2025, about the fundamentals of DCC wiring. There's a tremendous number of things you can do with digital command control, and wiring has an enormous number of iterations. However, I'm just going to cover the fundamentals. The basis of many of the things I'm going to say to you come out of Alan Gartner's book on DCC wiring that was published in 2024. Alan is an electrical engineer. He's written extensively about digital command control and writing. His book is available on Amazon for like $18 delivered to your door. And it's just absolutely outstanding, very well illustrated. And some of the images you'll see this morning are directly out of his book. Alan is a really nice guy. I've spoken with him, I've talked with him recently, and he's really considered the guru of DCC wiring. And that's some of the things I will say are the basis of this talk. I know there are many ways of doing this and doing it well. Okay, I'm going to show you the fundamentals. I'm hoping that somebody will take home with them at least a knowledge of all the fundamentals and how critical proper wiring is to proper DCC operations. Okay, now the goals of the presentation is to show why that wiring is important to critical to DCC operations. We'll explain proper wiring techniques, hopefully acquaint everyone with some of the tools necessary for layout wiring, and finally, in the end, to demonstrate and give hands-on soldering experience, the bus to the track, drop to the rail, and we're going to make those solder points. Okay, we will also be putting in the main power buses in the modules. In front of you here is a module that has been wired, and this is really the way we're going to wire all the other modules, okay? It's pretty fundamental, it's pretty easy when you look at it, but you've got to have the proper materials, the proper solder irons, and the proper approach to doing this. If you don't do it right, you're gonna pay a price. Okay, and there's the cover of Alan Gartner's book, and he is definitely the grand poobah of DCC wiring these days. There's other books out there. Mike Polsgrove wrote a very good book about 2016, and there's other work, but this is the latest and the greatest. When you're building a railroad, you got to start somewheres, and you got to start with a track plan, okay? And you've got to sit down and draw this thing out and draw it out to scale. I don't know how you get around that, okay? Any layout demonstrations, layout diagrams that you see in Model Railroader or model railroad craftsman, all of those things are drawn to scale, okay? And they just break it down so it fits on a page. And you've got to draw everything out to scale. If you don't, it's going to be very hard to actually build it and lay the track. I recommend that you separately draw out your table work, which we've sort of done here, haven't we? Okay? And from the table work, then you decide where certain things are going to go on that. But the table work is drawn out to accommodate the track, and the track plan is number one. You're going to put your wiring, hopefully, underneath. Where else? And you're going to have to get it properly supported. And I recommend when you build a railroad, you drill out raceways and lay the buses before you put anything on top. Man, is it a lot easier to do. Once you get the top on the layout, you now have to get out and get under and get underneath. It's a good practice and common sense to have your bus wires simply follow the track plan around. That will give you the shortest drops between the track and the bus, and you minimize the likelihood of signal loss or signal distortion. Okay, and we create the power buses under the layout, and that follows the tracks on top, and that's how you're going to get started. That is a track plan, ladies and gentlemen. Okay, this is drawn to scale. The scale is up here. Okay, this is my layout. This was drawn up before I built the layout. It was, and then I drew this up as an as-built for part of my Master Model Railroader achievement program, so that I could get I think this was drawn for the civil engineering certificate. Okay, but that's my layout, and when you sort it all out here, 1/2 inch to the foot, it's about 38 feet by almost 20 feet wide. So it's a pretty good size layout. Okay, and you sort of need to do it in this kind of detail. The wiring is going to come later. So, and the other thing you have to decide is, once you start wiring, is where is going to be the point source for all my power? Where is that going to come from? We recommend that you put your power cabinet or all your power sources, which would be your command station and your booster, to make it centrally located so that the length of any one bus is minimized. Now, you're not going to be able to put it exactly in the middle of your layout, but you have to pick a point where it's approximately, you know, no bus is that much longer than any other bus, and you minimize the length. Okay, and I'll tell you what the limits of that are. You'll notice over here, this little dotted line here, that is my power cabinet. So my buses, which sort of start around here, go this way, and then they come around and go this way, and they also go over to this segment here. Okay, they're roughly in a half. It's not quite, but it's roughly a half. When you're figuring bus length, don't figure just the length of the wire. Don't figure the length of all the track on top. Okay, it's only the length of the wire that counts. That's what you're putting the DCC signal through. Okay, you can see the type of materials I used. What you use, that's up to you. A lot of people using Code 87. A lot of people do not use Pico Insulfrogs. They use the Electrofrog, or they use another brand. This diagram could accommodate any of those things. It wouldn't make any difference. But more or less, you got to draw that out and have a pretty good idea of where you're going to go before you start, you know, drilling things up and buying lumber and plywood and all that stuff. Such as a power cabinet. Okay, a central location is advisable, as I've already said. If some of this equipment looks familiar to you, it should, because we have exactly the same thing here in the club. If you look over in the power cabinet in Piedmont, you'll find one of these guys here, DCS 240, and there's its power supply. These power supplies now, at least for the Digitrax world, have to be regulated power supplies by government regulations, and they're all DC. The early power supplies were virtually all AC, easier to build an AC power supply, cheaper, okay? But these are regulated power supplies. The difference between a regulated and unregulated power supply is a regulated power supply only delivers the amount of current that is being called for by the device it's powering. So that if you have a 10 amp power supply here, but you're calling for 2 amps here, it gives you 2 amps. It's running at 2 amps, that's all. Okay, and it doesn't give you you don't have the extra current there until you call for it. It's a regulated power supply. It is now a government regulation. Okay. I have some other goodies in here. I have a fan here. I usually put a fan on that unit. The units get hot, and they do have thermal protection. I have a power supply for all my LEDs, because I use twin solenoid machines from Pico to activate all my turnouts. And this beast over here runs this little guy back here, and he's a capacitance discharge unit, and that runs all of my turnouts. So I don't run the turnouts directly in DC. I run them off a capacitance discharge unit, which gives you minimal current, but maximum voltage. So you hear a quick snap, and then this does not reset until you release the button. so you can't burn up the solenoids. It's important that you get a concept of power districts and booster districts. There's a lot of confusion about this, and I find these terms not being used incorrectly many times. Every command station that you have, at least in the Digitrax world and pretty much in the NCE world, contains a booster. The command station is the boss. It generates all the digital command control signals. It also controls programming and a whole flock of other things. But it puts out the DCC signal at very low voltage, okay, and very low current. And you can't run a train with what's coming out of that command station alone. So we feed it into a booster. A booster is simply an amplifier. And that amplifies the DCC signal, brings it up to whatever you have it set for, usually around 14.5 volts. And the booster will also give you whatever current it's rated for, depending on the power supply supplying it. In the club, we use an 8 amp system. That's a lot of power. Most home layouts don't need 8 amp systems, okay? But although you can do it, it's okay. The NCE systems are only 5 amps. There is a 10 amp version. That 10 amp version is meant for large scale only, okay? And I got a stern warning from Jim Scores, who owns, operates, and developed NCE, that should not be used in HO, or most certainly not in N. If you have a short circuit or you have problems, you can burn things up. It's just not safe, and it's not necessary. So the DCC booster just amplifies the signal from that's generated by the command station. In any system, you can only have one command station. I've seen people try two. I saw somebody tried it here. It doesn't work. You can't do it. Okay? One command station has to be in charge, or it will not work properly at all. Okay? But one command station can be connected to many boosters. Okay? In the world of boosters in the Digitrax world, the boosters cannot generate a DCC signal. They simply amplify it. Okay? A booster in an NCE world can be one of two types of boosters. When I was visiting Jim Scores at NCE some years ago, I asked Jim, I said, what is the difference? You know, why'd you call one a DB and one an SB? And he said, it's really simple, Dan. He said, nothing is stupider than a booster. He said, it is the dumbest piece of electrical equipment you can think of. He said, all it does is amplify. It does just that. He said, but a smart booster, which is designed for their power cab system, it can actually generate signals. Once it has a signal, it remembers what it is, or what the series of DCC commands that it has, and it'll keep repeating those and repeating those, even though the power cab is disconnected. So if you want to enlarge a power cab system, you need something from Mr. Scores that starts as an S, with an S in front of it, an SB, or smart booster. You then have to do something about the output from a booster, okay? And generally speaking, you need to put this through a device called an ECB, or an electronic circuit breaker, okay? In this club, we use PSXs, which are made by DCC Specialties. The short circuit protector will very, very rapidly uncouple the booster from that power district, so that you will protect your equipment, and it will identify and isolate a short circuit to a given power district. You can have many ECBs can be connected to a single booster. Many. You could have, 15 or 20. We have, in Piedmont, we have 7 PSXs plus reversing units. We have, I think, at least 3 reversing units in there. And every one of them constitutes a separate power district. So that's 10 power districts connected to one booster. We have a similar situation in Asheville. We have at least 8 power boosters. power districts, again, from one booster, okay? One of the questions that sometimes goes up is, well, in any given system, in a very large layout, how many boosters can we connect to that command station? Okay, because we can daisy chain them along. Jim Scores told me the story that some railroad club in this country, I think it was somewhere in the Midwest, tried to find that out. And they got into the hundreds of boosters that could be connected to a single command station without a degradation of signal. That is absolutely amazing. And it shows you how good the DCC signal is in his system and how good the boosters are in terms of taking it and then passing it along to the next one. Okay? Not unusual for great big layouts to have 3, 4, 5 boosters. And many ECBs connect to a single booster. Each ECB constitutes a power district. The electrical bus connects to the ECB through a DPDT switch. Okay, and if you'll notice all the big switches on the panel out there, they're the DPDT switches, double pole, double throw. So that when we turn the power off to a bus, we kill the power on both poles to that bus so you can work on tracks, isolate short circuits, whatever. That is a schematic of what exemplifies the fundamentals of a whole DCC system. Okay, there's only one thing working in here that we didn't draw in. Well, wait, it's actually in there. It's the ramp meter. I didn't talk about that. But we start over here. We plug it into the wall. That's a power source. That's an older one, a Magnafor 615. It gives about 15 volts AC to a DCS 100. DCS 100 and 200 can take AC, and so can an NCE system. Okay, and then out of that comes your rail A and rail B. We put it through a meter to measure the amps and the volts, and you need a special meter for this. Okay, you need a meter that can handle RMS signal volts, root mean squared, or peak to peak. And if you don't have that type of meter, you're not going to be able to accurately measure the volts and the amps in a DCC system. The ramp meters take care of that. They're very, very good. Cost about $50, $55, something like that. And they're made by the same company that makes the PSXs, the PSXX, and the PSXAR. Okay? You then can feed that signal coming out of the ramp meter to any one of a number of ECBs. Okay? The electronic circuit breakers here can be daisy chained for as many, typically as many as you need. And then we also can daisy chain the PSXs. Same thing. The boards look similar. They're not similar. They're appropriately labeled. And then the PSXs, let's take number 1 here. All the power output goes to a DPDT switch, and then it goes out to power the bus. And that pattern is duplicated in all of the other power districts. And we do the same thing here in the club. There's really no difference. Okay, and that basically gives you the fundamental architecture of a DCC system. Yes, Tom?
So that switch that you're talking about?
This one?
Yes.
Yes, sir.
So when you turn that, is it a double switch?
It's a double pole, double throw. Yes, it is, Tom.
So there's 2 switches on that?
There's no, well, it's switching both sides.
So
you do it in one switch.
Okay. Okay. So when you turn that on, that actually gives you the power to your
to the rails.
To the rails.
Okay. That's what stands between, the power to the bus and therefore the rails and the ECB is that.
And with the PSX, that would give you a certain section of your layout. You can break it down into sections so that if you have a short, you know where it would be then.
Yeah, it's to help with location of shorts, and it gives you a measure of safety. Short circuit situations can be very damaging to your locomotive. There's a couple of amps flowing in there, and we've had locomotives that have, in serious short circuit situations, that have lost their program. They lost their address. It had to be totally reprogrammed. Okay, it's not a small thing. And the whole idea of an electrical bus, just like a real bus, is that it will carry something, in this case power, to all devices connected to it. And that's what a power bus does. Just like a real transit bus that goes down the street and lets passengers off at stops as it goes. And an electrical bus is very analogous to that. The nice advantage here is that the bus really, which goes to a number of track segments, can be, simplifies your DCC wiring. You now do not have to set up a number of electrical blocks, okay? And your wiring is actually less rather than more. It's a serious improvement in wiring. Initially, when DCC came out, they said, oh, just put one power bus around, you connect it all, you're done. Not quite that simple. Some layouts are just too big for that sort of thing. Okay, now one of the questions is, you know, where and how do I run the bus? Okay, we've already mentioned under layout, you got a better place? Well, I don't. Okay, but you don't put it along the sides. You can pick me up on this. You don't run it along the sides here. Okay, that's reserved for your LocoNet or your cab bus. You run it in the middle. You've created raceways here and connected to Euro connectors, which I'm pointing to at the ends. You can then tap into those Euro connectors either from power source or from the next module over or whatever, okay? But that's your power bus. You now can create track drops to that, okay? Each bus is simply a pair of wires. The bus is needed, you need a bus for every power district, okay? And it just should follow your mainline track, or if you're powering a yard, you sort of try to get it in the center of the yard, but you can loop it around. You can run it in a couple of different places. That's okay. That does not break any rules. I really recommend they be run in raceways. You line up all the holes just as they drilled holes here. Generally speaking, we draw a little bit bigger holes, but it's good enough for what we have. It's fine. Use a different color-coded wire for each bus is a recommendation. That may be hard to do. Wire gets very expensive, particularly if you're using copper. You know, my recommendation is here, well, you've got to use two different colors for a bus so you can distinguish one pole from the other. You really need to label your buses. Give them a number, give them a name, give them something. Numbers are easy to work with. You can give them letters as well. But number them underneath your layout relatively frequently. Your label machine will take care of this very nicely, and you make up labels and throw a bunch in. You do it once and you're set for life. Okay? On top of the layout, up above, you must double gap the track between power districts. Absolutely. You cannot have one rail connected and one rail not connected. That's a serious no-no. And you must use insulated joiners. Do not simply cut the track. Say, oh, this is the end of this. I'm going to cut the track with a nice Dremel cutting tool. Hey, it looks great when you do it. It'll work until there's track movement because of seasonal changes, temperature and humidity variation in the environment that layout is in is going to make that track move. And it will reconnect at one point, or one side will reconnect. And suddenly things are kind of screwy, particularly when you have a short circuit. Okay, so use insulated joiners. Okay, now there is some issues about how long can your bus be. Okay, the bus length is recommended 25 to 30 feet. It depends on the gauge of the wire. We'll see that in the table that's coming up. And it is recommended by some people that you give it a twist 2 to 3 times for every foot. Now, in a very small layout, in a very small situation, I don't think that's very important. I really don't, and I don't think anybody else does. But if you're in a big layout, like we have out here, okay, you got to twist that bus. The main buses in Asheville, I twisted these in the most amazing things. I had somebody stand by this door here, and then I took, I don't know, 100 feet of wire or something like that. I put it in my drill bit, and I just pulled the trigger. And that did the twisting, okay? The insulation is vinyl, it has memory, it will untwist a little bit. Eventually it will develop a new memory and you'll have the twist will be relatively permanent. This minimizes signal spread and crosstalk among wires, and you don't want that. NC recommends snubbers. I'm not going to go into what snubbers are. They're basically a small resistor and a ceramic capacitor. Digitrax does not, and I leave it to you. We tried it here. We took them out. Didn't make any difference. A lot of it has to do with the actual DCC signal, and you need special instrumentation to actually see that. You need a high-speed oscilloscope. The DCC signal at the top where it turns to go down, and we'll see that in a slide coming up, may have a little distortion at the top. It's not a perfect square wave. So that distortion, depending on what it's called, is called ringing. And NCE boosters have a lot of ringing at the top. The fun part about that is, as soon as you put a locomotive on the track and remeasure that signal, the ringing goes away completely. It just needs a little bit of current draw. Don't ask me why that is, but somebody has gone out and measured that and looked at it. Okay, let us keep going. Signals, okay, and this is why the wiring here, this is so critical to proper operation, okay? This slide shows 3 individual types of waveforms. First of all, we got just the flat wave here from a frame DC. And the flattest and smoothest DC comes from a battery. If you have a battery and you measure that DC signal, it's going to be flat as a pancake, okay? A signal that goes through various filters and rectifiers will sometimes have a little bit of ripple in it, but it's usually more than good enough to run a DC motor. We have over here the AC waveform, a perfect sine wave at 60 hertz, or at 60 cycles per second. That's what comes through the wall in our electricity. The thing about the wiring that's all around us is I can measure 120 volts on every person in this room. Okay? It's on your body. And if you've gone to the doctor and you've had a cardiogram, or if you've been, you had your colonoscopy or whatever, your cataracts, and you've been monitored, that monitor is actually pretty sophisticated because it has to eliminate this AC waveform that's on your body. And the way it does it is with a pair of differential amplifiers. And it's dealing with a situation whereas your cardiogram generates a millivolt, this is a full volt. That's 1,000 to 1. So it subtracts the 60 cycle AC on one side, 60 cycle on the other, and you get the net is your cardiogram. But this is all over the place, okay? And there is no way you're going to get rid of it. Out in the middle of the desert, I'm not sure. But one of the issue here is that electrical fields from an electrical wire are fundamentally infinite. Okay, they've never really measured it, so that the electrical field generated by, say, high tension wires goes way, way out. It might go, and you can measure it at some enormous distance. It degrades according to 1 over the square of the distance. Okay, so it degrades rather rapidly, but still it's there. Okay, DCC, here we go, babe. Okay, it's a square wave. It's made up of 0 and 1 bits. 0 and 1 bits have a finite duration. And there is the NMRA has defined what the standard is for this wave. And the 1 bits are shorter than the 0 bits. The 0 bits can be stretched. Stretch them too much and we can actually run a DC motor. But there's a limit in these. And there are instruments, and I own one, to measure the length of your 0 bits, your 1 bits, bit errors, positive errors, negative errors, the whole 9 yards. But that's your DCC signal. But it's really rapid. It's running at 7,100 hertz. So we go from 60 hertz over here, 60 cycles per second, to 7,100 over here. That is a huge leap, guys. Okay? The DCC signal is absolutely unique in the world of electronics. There is no signal like it. I have that from one of the developers, and I assure you that that is, to my knowledge, still correct. So the DCC waveform has to be perfect out a fair length. This is why we need heavy gauge wire in our bus, and we only can run that bus so long before this starts to break down. When this breaks down, your decoder, which is in your locomotive, which is basically a signal processor, cannot read it, okay? It looks like gibberish to it if it's really distorted. The packets that's sent out include a checksum. And if the checksum and the address, they don't match, or the instructions don't match, the decoder ignores them. And if you miss a couple of packets, often a motor, the DCC unit will just stop running. Okay, that is the way the thing. So there's limits here. We have chosen to use a 14 AWG here. Okay, in a 5 amp system, your signal's good to about 40 feet. That's what that chart tells you. Okay, that's sort of the max. If you go over it, it's down to 20. Okay, so by making our buses maybe 30 feet or so, we've got some headroom in there, and we've got a pretty good safety margin. Okay, if you're running a 12 gauge bus, okay, you certainly got a lot more feet because it's a heavier wire, and there'll be less signal distortion won't start until you get out to around that point. Yes, sir?
I know you wanted to wait till the end, but I have a question. When you're talking about the feeder wire to the power source or the individual leads from the track?
I'm talking about, this is the bus. This is your bus length.
What's the main line coming out of the bus?
Yeah, coming out of your ECB and running into your layout. That's what this is talking about, okay? And as you can see, as you get to smaller stuff, you're not going to go very far, okay? But, you know, on a tabletop layout, I mean, you could certainly use 16 and you get away with it. That'd be absolutely fine, okay? And this chart shows the max for a half-full drop, okay? Once you get a half-full drop, you're going to start getting signal distortion, okay? This chart has been worked out empirically. This is measured stuff. This isn't something that somebody made up theoretically. These are the track drops. You asked about track drops. You know, how long a track drop can you have before you start having problems? I typically don't do track drops any more than about 1.5 feet or 18 inches. Now, you can get away with larger than that, and again, it depends on the gauge of the wire you're using, okay? In our layout here, and in the stuff I'll show you here, I have chosen to use a 22 gauge wire. This is for HO scale, 36-inch flex track. Gee, that's exactly what we have. Okay, so the Y in the end is how long can you go without having signal distortion or voltage drop? And you probably can go out to about 3 feet. I cut that in half and go to 1/2 foot, so we're fine here. And if you're an N scaler, we come down here, you certainly can get away with a little bit more, and you'll get 22 gauge, you'll be fine, and you can use 24 gauge up to a couple of feet. You won't have a problem. You will have a problem after that. The N is a no-no. Is that clear to everybody? This is really important stuff when you're building a layout. You have to take this stuff into consideration, or you're going to have problems with operation later on. It'll definitely come back to haunt you. Okay, the track drops get soldered in 2 places. This is a typical joint from a track drop here to the power bus here, okay? Now, what Alan Gartner says is true. Of course, soldering does take more time. It's fussier to do, but it gives you a much better connection, I believe, than anything else out there. There's other ways of doing this that are faster. If you do it right, it'll work. How long it'll work, I don't know. Okay? And it says here, make sure the iron heats both wires. Okay, the lighter gauge feeder will become hot first. That just makes common sense. I solder these things into the track at over 700 degrees. I do not solder with 25-watt solder irons like you buy in the big box stores. I solder with regulated stuff, and I solder at very high temperatures. and with very small tips on my solder iron, so that I'm concentrating all the heat at a very small point. The point is where you want the solder to be. And you know, you'll sometimes get a little burning of the insulation here, and you can see it's a little bit burned there. But if you wrap it around, he's used he didn't use stranded wire, he used single filament wire. I like to use stranded wire. I think it's easier to wrap and easier to work with. It does require one other operation, but either one will work equally well. And incidentally, as an aside, there is no difference in conductivity between a solid wire and a stranded wire for any given gauge. However, the stranded wire is going to be a little bit thicker and a little bit bigger, just a little bit, because there's air spaces between the filaments in there. Okay, so it'll always be a little bit bigger. You can hardly measure it, but it's there. But the conductivity is the same. Okay, there are other ways of doing it. These are the so-called suitcase connectors. I labeled this the quick and the dead, because you're going to get, Kevin is shaking his head. When I asked Alan about this stuff, he pointed out, he gave a talk at up in Gatlinburg when we were just there. And, you know, I asked him about this, and his feeling is that, you know, people are using these, they're very popular, they're certainly quicker. There's no question about their speed. But, you know, it's sort of like what somebody said, if you're choosing an ophthalmologist, don't choose one that works with blinding speed. So, okay, sorry. But truly, the connection here is not considered as good. I remember some years ago, I was at Tony Custer's layout in New Jersey on a tour, and he was trying to operate his layout, which had just been redone at the time, and all of a sudden he says, "I don't have any power over here. Nothing's working. I don't have any power." And Tony Custer loves these things. I walked over to a great big bridge. That's where the power was dead, and there was one of these things lying open. The thing had opened up, and they will open up. You've got to use a proper crimping tool when you use these, and you must see the two holes here. You must put in those the wire gauge that the suitcase connector is designed for. It tells you on the suitcase connector. You don't have to guess. But if it's for, you know, 14 and let's say 18, and you put a 22 gauge wire in that, you're not going to get contact that's worth anything. You've got to get the gauges have to be absolutely matched to the specifications of the suitcase connector. And this is when you get them in, this is sort of what they look like. Okay? It does save you soldering. I think there's, you know, it's a hobby, it's not a race. So we're going to start with, first of all, some of the tools that are needed. Left side here, this is a calibrated solder station that will give you very high temperatures at the tip of your solder iron. It measures the actual temperature, and this can be calibrated for that temperature or any given temperature. Okay? The number you see is the degrees Fahrenheit. This particular unit goes from somewhere around, I think, 350 or 400 at the low end up to 879 at the high end. I tend to solder at relatively high temperatures and using a touch and go technique to concentrate all of the heat at a point to do it quickly, to get that solder to melt, get that joint done, and get out and do it very quickly. I have a second one here on the bench that does fundamentally the same thing. These are some of the tools you might use and you're going to need for wiring, and it's only some of them. These two here are different sizes of wire cutters, or what we simply refer to as a cutter. So when I ask for a cutter, it's one of these babies, okay? Okay? Sometimes a long nose will have a cutter built into it in here, but these are much better cutters, okay? This particular crimping tool is for Loconet. This is for the Telco connectors, and we use this for Loconet. I'm not going to talk about Loconet, but this is the type of tool you use. This particular tool here which is this tool here, which I'm holding up, is a stripper. It will strip everything from 22 gauge wire up to about 12 gauge wire, okay? And when it comes together and strips, you must put the wire you're stripping into the appropriate slot to properly strip. If you get it in a too large an opening, it just won't strip properly. If you get it in too small, it'll cut the wire, because these things are very, very sharp. And I use this to spread the insulation on the bus when we do put the connections from the track to the bus. Okay, we got some more tools here. You're going to do electrical work, strongly recommend some kind of multimeter. This is one by so-called Ideal, made guess where. But it's a digital meter. You don't need to set scales on it. It'll automatically knows what scale it needs to be in. So if you measure 3 volts, and then you go over and measure 240 volts with the same thing, you got to go from AC to DC, it's fine. It's all fine. And it can also measure hertz. So if you're running when I run my generator at home, if I want to check the CPS, I just put this into an outlet and set it for CPS. Okay, it can measure current. It has an audio alarm on it too for short circuits, and you can measure ohms. And again, just set it for ohms. It'll figure out what the ohms are and give you a digital output of it. They're very, very good. I really like this one. I've had it for some years, and it's held up really well. Okay, you're going to need some wire ties. You're going to need a stapler, and I recommend a label gun. That's for labeling those buses or anything else, or Euro connectors. And keep your stuff labeled so you know what it is. You quickly can get confused and forget over a period of time. Now, if you're going to wire, you need wire. Okay, examples here are, this is the 14 gauge wire we use for the bus. This is the 22 gauge wire. From All Electronics, I buy this. I used to buy this from them in 100-foot rolls. You can't do that anymore because there's no more All Electronics. They're out of business. They were in Van Nuys, California. And this here is your ribbon for DCC. Your Euro connectors. Kevin has another name for them?
Phoenix connector.
Phoenix. Okay. They're a barrier strip. You can use barrier strips in place of them. I like these because you just stick the wire in and tighten the screw. They come in many different sizes. I've got 3 sizes here demonstrated. And also, you know, when you're building a layout, you're going to do some programming or whatever. It's nice to have a computer. This is the laptop you see here is the one that's running this show. And that slides out from underneath my layout. You can see the USB connection, which goes right into my command station directly. You don't need an interface with a DCS-210 or a DCS-240, the old interface being a local buffer. You need a local buffer with the earlier models from Digitrax, but not with the new ones. He put the interface is all built into the command station, and it's what they call opto-isolated. In other words, there's no direct wire connection, so you're not going to burn anything up one way or another. Very, very well made. Okay, a quick review here of where we've been. Okay, the command station, the booster, we connect the throttles here. Okay, the booster feeds the ECBs, the electronic circuit breakers, and the circuit breakers go right to the bus that goes all the way around. It's showing you 2 power districts here, and note that the track, which is the dark lines here, are double gapped. Okay, and that's kind of schematically the way that things work. Okay, and fine. I got to say a word about reversing circuits. Okay, I didn't really cover this earlier. Probably should have. You got to look at your track plan very carefully and decide whether or not you got reversing circuits in it. If you have a single track layout that comes back on itself and then you decide you want to crossover at some point, you've created a reversing circuit. If you have a turntable, you've created a reversing circuit. And sometimes the reversing is very subtle. It's not obvious until you start running the trains and you got these unexplained short circuits when you go through certain routes. okay, you probably have created a reversing circuit without realizing it. But anything that will reverse, okay, the travel of a locomotive is a reversing circuit, okay? And you can look at that and trace it out. This is a schematic of the reversing circuit. I'm sorry, I missed down here when I did the photography. That's an auto-reversing auto-reversing device like in PSX AR we use on the layout. This is the main bus here, and this feeds an isolated segment. You know this is a reversing circuit by following one of the tracks around. Now let's take the red track, we follow it around, we come through the crossover, and oh my God, it's now a black track. Okay, so you connect that up, you're going to have a dead short. If you don't isolate with double gaps at either end, your reversing section, make sure your reversing section is long enough to accommodate the number of locomotives or the size of, if you're running lighted cars. Lighted cars are, you know, they're like a locomotive, really, electrically. So if a lighted car is across this segment here, with the back wheels here and the front wheels here, and we come up in front here, and the locomotive is here, with its back wheels here and its front wheels here, your reversing segment is you're going to have a short circuit, your reversing segment is too short. Make sure you make it long enough for the trains that you want to run. Okay? Kind of important. Okay, but that's the way those work. We have multiple ones in the Apple Valley, and you don't know that these things are reversing. They happen so fast. It's millisecond reversing. They're solid state. They do not use relays, and not really anything that you even notice when you're running the trains. Yes?
Can you go back to that slide a second?
Absolutely.
Okay, right there where the G is.
Yeah.
Okay, prior to that it's red and then it turns to black.
Yeah.
Could you not take the wire off the red before the G and run it under the black wire and connect it to the red on the other side? Would that eliminate that?
No, it would not eliminate it. You're still going to, your path. See, if you run a locomotive in this direction, coming around here, okay, you go through this, and you now are going in this direction, guess what? You've reversed the path of the locomotive. So that's a reversing section. Yeah, okay. Yeah. We used to, you know, in DC we used to use, you know, a lot of double pole, double throw switches, and you'd have to throw switches back and forth and back and forth. And Atlas made some stuff that would help you do that, but that's a real pain. This is now fully automated and works at literally at blinding speed.
Hey Dan, go back to that.
Yes,
again.
sir.
So there, at G and H, there is a gap in the...
That double gap at the rails. Yes.
At the rails. Is there any kind of connector to that?
Yeah, insulated connectors. You use insulated connectors here. You would need 4 insulated connectors to replicate this, 2 at each end.
Rail jumpers.
I have 4, you know, well, you got 2, right.
So the actual rail is not touching each other?
They can't be touching.
Okay.
They absolutely cannot be.
Okay.
Okay, and the insulated connector will maintain the gap, Tom. Okay, you don't just go in and cut these. You have to put an insulated connector in, and you have to anticipate this when you build your layout. And again, there's a whole, the admonition to go back and look very carefully at that track plan to identify reversing circuits and how you're going to make that work.
And how big is the gap?
It just has to be discontinuous.
Okay.
There's no minimum.
Okay.
But an insulated connector, I'd say it's a couple of millimeters maybe. It's no more than that, as long as they're discontinuous. And by the way, if you build a layout and you ballast it, and you go through these things, and oh my God, you got short circuits all over the place. That's because the ballast uses water, and the water is conductive. You got to wait for the ballast and the glue to dry. Once they dry, you'll be fine. But that's a famous mistake that people made. They go out knocking themselves out to find, where's the short circuit? I've got a short circuit. I didn't have one before I ballasted. Now I got one. I just ballasted, 6 hours ago. Well, it isn't dry yet. It takes a good 24 hours or more for ballast to dry, for that glue to dry and get the water content out of there. Solder is an alloy. It's a very, very unique alloy, okay? And it's made up usually of tin and of lead, and that's a typical percentage. Now, there's a lot of people that say they'd like to, as it were, get the lead out. And some people are substituting copper in here. I've seen one place where somebody used non-leaded solder, and it just didn't work very well. It's not very good. So most of the solder that you're going to buy is this. Do not buy acid core solder. Please, you'll ruin everything. You buy stuff for electrical work. That's what they sell in the big box stores anyways. The acid stuff and a lot of other stuff, what the plumber uses is not what you want to be using, okay? And that's a typical ratio. But you've got the problem that you know, you need to melt it at a relatively low temperature compared to the melting point of the individual metals that make up the alloy. Tin melts at about 449 degrees Fahrenheit or 232 C, and lead melts at 620 Fahrenheit or 327 C. But when we put them together as an alloy, they melt at 361 Fahrenheit or 183 C. And that is known as the eutectic point. Okay, and solder sort of gets the nickname a eutectic alloy. Okay, because the solder, the alloy melts at a melting point lower than either of the materials that make up the alloy. Okay, it produces a so-called change of phase, solid to liquid. That's the melting of the solder. Okay, at a certain temp, and that's called the eutectic point. And that's the way that's defined. I had to do this in college, and we did a whole bunch of things with that. Let me talk about fastening the track drops. Okay, we're going to start track drops by drilling holes. Boom, boom. I have a 7/64 drill. It'll take me 5 minutes to do everybody's here. Okay, you can do I'm going to do one. You're going to do the rest. Your modules. Okay, you drill the hole in between two ties. Do it at a place convenient where you can reach, by the way. Okay, you then take a flat X-Acto blade and you take off one of these tie plates. Now, I don't show the tie plates on the outside. Tie plates are on the outside and inside. There's one on the inside there. It's absolutely duplicated on the outside. But you have to cut it flat to the top of the tie. That's all. And snap it off. You only do one. You do it right next to where you drilled the hole. So here, if I were putting a track drop in, I'd knock off that tie plate, okay? And you do it with an instrument like that, okay? And I have one of those with me. You can see the hole on the other side over here. Now, I'm showing you track that's already been, you know, ballasted and all of that stuff, but it's the same. You do the same thing. It's a little easier when it's not ballasted. At the point where I'm going to make the connection, which is where that tie plate has been removed, I polish the track to get off any paint, in this case, or oxides of the metal, to polish it and polish it clean. That'll help give you a much better solder joint, okay, and a quicker solder joint. I then go ahead and put a little flux on this, solder flux, and I tin that. Again, you must tin it at high temperatures. If you don't, you'll melt all the darn rails. But you tin it at high temperature, and that is a serious close-up of that, okay? You don't see that kind of detail when you get a few feet away from it, okay? You tin the area with the solder. Be careful not to melt the tie. If you keep the point of the solder iron on the rail and you do this quickly, it's not likely that you will melt the tie to any extent. You might melt a little, but not very much. You're going to paint it and ballast it afterwards. You lose it when you see it. You won't even know where the drops are. Okay, I then take one of my track drops. You strip them short at one end and long at the other. Okay? The short one is the one that's going to go next to the track. You're going to bend this at a right angle. Don't have a long nose out here yet. But you bend this at a right angle and then bend it back. Make it look like a hockey stick. And you clip it. I use a small hemostat for this. That's called a small cryo clamp or a mosquito clamp. And you clamp it where you to the rail channel here where you have tinned it. Okay, now this wire has been already pre-tinned, and so is the rail. So we got a lot of solder already in there. So it's not going to take a lot of solder in addition to what's already there to get a good solder joint. We then go ahead and hit that with a solder iron, and we get that, and that's what you see here. You see it right on that. See, what I did here is done exactly the same way as this one. No difference whatsoever. This looks doesn't look quite as neat because it's already been ballasted, but that's, it's an equally good solder joint. Okay? Good soldering techniques are really important. Okay? And I say this, I say, well, solder schmotter, but it's you only want to have good soldering techniques if you want to run your trains. If you don't want to run your trains, it doesn't make any difference. Okay? Good soldering techniques, a proper electrification and effective operation of a model railroad, especially one powered using digital command control, where we don't want to get distortion of the signal because of lousy connections. Okay? Now, for all this equipment that we're showing you, okay, and everything that's up here, there's no question that, you've got to make a little bit of investment, and it's going to cost you some dough and maybe a fair amount of bucks.
This is one instance where the bigger the glob, the better the job. It does not apply.
No, it absolutely doesn't. Less is more. You certainly, would like your railroad to run like this one. Those pictures were taken out here a few weeks ago. And in the end, guys, you want to make a railroad that not only looks good, but that really runs well. Okay? Looking good is one thing. I've been to some layouts. I was up repeatedly to one up around Chappaqua, New York, when I lived in Connecticut. Guy had this gorgeous layout. Spectacular. Okay? Tremendous scenery, beautiful buildings, and whatnot. He lived near where the Clintons lived, by the way, is where he lived. And the house then had to be $2 to $3 million. Nothing ran. I never saw a locomotive run, and I was told, it doesn't run, Dad. They didn't do the wiring right. And he spent all this money on it, had a lot of friends in, but nobody knew how to do wiring. So, we'll do wiring later. Don't worry, it's not important. It's fundamental, and you do it while you're building the railroad, and do it, for God's sakes, before you put any ballast or any scenery down.
For more information about the Apple Valley Model Railroad Club, visit their website at avmrc.com.